How was y'all's weekend?
Bueno.
Bueno? Okay, what'd you do for fun, Lucas, with all your siblings?
I went to the basketball game Saturday.
Oh,
You left the basketball game?
I'm going next. I'm going this
We went
weekend.
to the baseball game on Friday. I was here, but I'm sorry, I didn't know that was there.
It's okay.
Chloe, did you guys have softball friend? You went to the softball game. Is it before or after this one?
The same time.
I don't know if they play in the same field.
I don't think we do, but I feel like.
No, but it's just so distracting.
Yeah, it is. And I'm not a fan of it.
They've always been fun.
Yeah.
My dog and Ellie sleep past 7 o'clock. Savannah, what'd you do? Work. Karate? Oh, they were. I don't know. That's right. What'd you do, Allie? Oh my gosh, Allie. Nothing? That's a little bit, that's lame. Okay, we cut down trees,
Whoa, wait.
and then,
Chop down trees?
yeah, I would just watch mainly. And just
Why'd
kind
you
of
chop down trees?
because we just needed some more sunlight on our grass so the grass would grow. You know, that's how it works. And got my husband a broom kit this Christmas.
And
We started yesterday. I think it's kind of cool. A lot of science.
Oh, what kid?
Brewing.
Oh.
So.
What did you brew?
An alcohol-related beverage.
I'm just curious.
Yeah, it doesn't have any alcohol in it yet, guys. Yeast haven't done their thing.
I was just
Okay.
like, I'm curious, like, what was your end goal?
Okay, citrus, lemongrass, something like that. So. Alright, so I'm sure you're in the middle of an FRQ. Put your FRQs to the side. Put your FRQs to the side. Scantrons to me for the 77. Put my image to Jeff. Yes, the last two were FRQs, so 75. Hold on to your other parts for now. Helping.
Oh, I need to do
I have the thing that this thing.
Thank you. Put it in the box for you. Alright guys, and then I think I'm going to take about 10 minutes or so to go over bond energy and how does that relate to delta H. It shouldn't take very long, but we're doing this as like kind of a review and pulling it into Lewis dot structures because we've already done delta H stuff. We've already done bond association. So Riley, I'm hoping that you did that back with Mr. But we will review as we go, okay? So somebody be the bond. Be the bond. Okay? Bond association energy. Woo! Okay, endo or exo? Endothermic. Okay, so you can sit down here. You're good. So the more electron rich, let me make sure I'm videoing for my viewers at home. Hold on. All that YouTube money. Oops, that's not it either. You okay, Sean? Alright, so the more, with me, the more electron rich the bond is, that basically means that you have single bond, and then more electron rich would be a double bond, and the more electron rich would be a triple bond. The blank the bond energy, the greater, okay, so bond energy is always published as a positive endothermic value because we always are talking about bond dissociation energy. It just says bond energy, but it means bond dissociation energy. And then the correlating with this, the blank the length, shorter the length. And so we would say that the internuclear axis is shorter, or the internuclear axis, or the distance between the nuclei, is closer together. So try to use some of your terminology. Internuclear axis is shorter or closer together. All right, so as we are looking at these, you should be able to draw your structures very quickly and then determine the bond length. And then we can correlate that kind of to bond order like you did with your molecular orbital theory, but we are not drawing those molecular orbitals. We're doing it based off bonds themselves. So when you draw this, have you guys drawn these? Probably not. Draw these now. Draw those all now. Count your valence electrons and then go from there. Consider resonance. that that OH is an alcohol group, so it doesn't need to have an OH on the end by itself. Keep going. Should be a process that you're getting the kind of hang of. You're noticing a lot of times nitrogen will do a what kind of bond? Triple bond. Many times, not all the time, but many times if you have to allow for it to, it generally creates a good formal charge for it. So like for example, this nitrogen here, what's the formal charge around it? Or what is the formal charge of it? 0. Why? Who said 0? Go for it, Kirk. Explain.
Because if you count like the bonds, the single bond as a single electron,
Mm-hmm.
and then the doubles
Or the lone pair.
Probably 2 electrons.
Right, so there's 1, 2, 3 from the bonded pairs, 4, 5 from the lone pair. So there's 5 electrons assigned to nitrogen there. How many should be assigned to nitrogen based off the valence? 5. So 5, 5, there's no difference. That's our formal charge of 0. And this one over here, 1, 2, 3, 4, 5, there's 5 electrons assigned to it. There's a formal charge of 0. What about this one? Formal charge of 0. 1, 2, 3 from the assigned bonded pairs, 4, 5 from the lone pair. So when you're assigning it, you're counting half of the bonded pair and the entire lone pair for your formal charges. So all of the nitrogens are a happy formal charge of 0. So overall, with this like on the screen structure here, this +1 overall charge is stemming from a deficiency of an electron on the assignment of oxygen. So overall, what does oxygen have assigned to it in the structure? 5, 1, 2, 3, 4, 5. How many should it have? 6. So it has a deficiency of 1 valence electron. So that's why it has an overall formal charge of +1, which gives us the overall structure also having a +1 charge. So remember, the summation of formal charges should equal the summation or the overall charge of that molecule. So we've kind of drawn them all. Did you guys struggle with any of these?
I struggled with the no, I did H2O because I didn't realize there was N bond, and I just did like
Yes.
would need to apply.
So sometimes you'll do N bonded to O bonded to N, but the formal charges don't work out as nicely. So we have high charges, which would be unstable because we have too many high charged formal charges. So many times if you're bonding nitrogen, it will also bond to another nitrogen to create a triple bond or something similar. Yeah.
Why does the, why are both the bonds not double bonded in those?
Because formal charge would stay 0 if possible. So, and also nitrogen commonly will form a triple bond with something, but it normally doesn't double bond both sides. There's some, if you've done enough Lewis structures, probably seeing some patterns, you probably will never see a double bond on both sides of nitrogen because it doesn't hybridize that way very well. Okay, so we kind of see that there's some with some resonance structures, so we need to assign our bond lengths to these and then some strengths. So let's do the shortest to longest bond. I'm going to go with black here. So let's do the if you had to assign a length to this, I would call this a single bond between nitrogen and oxygen because there's no other alternative. So that's a single, so that's a long single bond, right? And then for this one, between nitrogen and oxygen, yet again, single bond. So we might have to fight ourselves on trying to determine which is a longer situation based on the environment that it's in. This one we have a triple bond, so it's certainly the shortest. Then we have some of these over here that we have to assign based on the resonance structure. So I drew both of the resonance structures here for nitrite, but what truly is the length of this bond when you do a superposition of that? 1.5, right? Because the double bond's not there. It's not actually there either. It's actually in both places. It's a blend. And so it's not this or this. It's a combination of superimposed on top of each other. So this is a 1.5 bond. So is that longer or shorter than a single bond? Shorter because it's closer to the double bonded side of things, so it's getting stronger and shorter. And then what about this one? I could have drawn this 3 different times, right? With the double bond in 3 different places. So what would that superimposed overall 1.33 bond, right? Because basically you're taking this bond and splitting it in 3 places. So that extra double bond, the extra bond you put on here, could have been here, here, or here. So it is going to be split into 3. So if you had to order these, which would be the shortest? For sure, this one triple bond that we have here, right? Or 2 triple bonds. So if you had to figure out which one was shorter, I would go with the one that, actually there's only one triple bond here. Sorry, I'm looking at this. It's got to be this one, right? I was looking over here for some reason. So first of all, the triple bond is the shortest, and then why the 1.5? Right, so then the 1.5 bond is going to be the next shortest, and then the 1.33 bond, which is the next shortest, and then you have to fight between these two, between this single bond and this single bond. So I would probably say, due to the structural components of this having an oxygen that's not sharing its bubble, it's a electron cloud more with a like hydrogen on the side, it all kind of pushes its electron density towards the center of this atom, so it ends up being a little bit more electron rich, which would be shorter. So single bond number 1 would be shorter, and then single bond number 2 would be the longest of them all. So basically, you can't get away from drawing. You have to draw these structures. I draw them still because I need to make sure that you're not assuming something correctly. All right, so whenever you're talking about the bond association energy or the bond energy, it's not just they took one atom and they said, oh, this is CH bond, this one is 300 kilojoules per mole. So what they do is they look at all the different CH bonds that are out there, and they basically do an average. So we have an average that are assigned basically to everything. So as a quick review, this is on your quiz, what favors bond formation? What's the purpose? What were we saying? Electrons what? They can still move, but they're in 2 electron clouds or 2 orbitals, so they're being shared to create octet. But I heard somebody else say something else. So the overall molecule in itself is a lower energy, right? So I'm gonna let you guys read this. Some of this was in your background reading. I'm trying to be too redundant because some of this we have already talked about. So this was that chart, that little dip one, where it was like really close together, Goldilocks region, really far apart. So the two atoms that were far apart were high energy. The two atoms were right on top of each other, were too close together, meaning they had proton to proton repulsion within their nuclei and electron-electron repulsion within their electron clouds. And then we have that perfect Goldilocks region where they have the perfect distance, where the protons of this one are attracted to the electron cloud of this one, and the protons of this one are attracted to the electron cloud of this one. It was perfect. So that energy is, of course, the lowest energy that these two atoms can achieve together. We call that lowest potential energy, aka bond energy. And that internuclear axis, or that distance right here, is the length that they take on, the distance that the bond length is. So we call that potential energy, that specific potential energy, the distance where the potential energy is minimal is called the bond length, which you can see from the graphs like this. They have this all the time, every single year on the AP exam. It's where the balance of Coulombic charge, attraction, and repulsion is balanced. And it's probably about it. That's the only process. We talked about energy lowering. That might be as a quick review. We've talked about much of this. Tell me when you're okay. I'm going to keep this up here because I know some of you guys are writing. I have a quick picture down here for you. Whenever you're talking about the H2 molecule, two separate atoms of hydrogen come together until they have the minimum repulsion with the equal stabilizing attraction that's occurring between them, and then they're going to achieve octet when they overlay their orbitals. So we've talked about this quite a bit. And then here's our little graph again. Too far apart, too close, Goldilocks region. All right, we're going to do one more together, and then I'll have a quick problem set so you guys can finish this in class. So normally, this is all jacked up in the back. It got really dark on the copier. But normally you can see a nice chart of bond association energies. What can you assume is going to have the highest bond association energy? What kinds of bonds? Triple bonds, and likely ones that are not only triple bonds but also the smallest atoms, because they get closer together. So not just nitrogen to nitrogen triple bond, maybe something smaller could get together. Oh, let's do this real fast. This is the part I wanted to actually get to today. So this was telling you that within methane, C to H bond has a bond association energy of there's four C to H bonds on methane, right? So if there's 4 CH bonds, super okay. So how would I determine if, but as I took my CH, and I broke it into CH, H, I broke 4 bonds, right? This is the overall process energy, which you can see is positive, meaning endothermic. So how would I figure out the CH bond energy? That divided by 4. Calculator? 413 kilojoules per mole of C to H bonds, because this is assuming that you have a full mole of it. Okay, so then overall, since you know that information, this is positive because it is an endothermic process. I'm taking C, Cl, and 3 H's coming together to make chloromethane, 1 chloromethane. What would that overall CL energy be? How are you getting that? Tell me your whole process. So I have these, I'm adding them together. I'm making CH, Cl. I know the energies of these. What are these?
It's 413 times 3.
Okay, so there's 3 413 bonds that are forming.
Just negative.
So yes, that's when we say bond forming is energy lowering. Why the heck is it energy lowering? Because it's exothermic, right? Because it's releasing energy. So these 3 bonds release 3 times 413 kilojoules per mole, which is how much energy? 1236 kilojoules of energy. Okay, so it's releasing, so it's negative 1236. If the whole process is negative 1578, what's the bond energy here? You have a calculator or use your brain. Don't sit there and look like a pretty person on a chair. I'm depending on you. My brain is I didn't wake up early enough this morning to kickstart it, so I'm working on this.
That's 12:39.
Is that 12:39?
Yeah.
I like to believe Alvin occasionally. Only rarely does he get things wrong off the top of his head there. All right, so 1578 was my total.
It has to be changed 3 times in 12:39.
So how do I?
Oh, is it?
413. What?
No.
Okay. Yeah, I'm using this energy up here. So the difference there, that is total. Subtract a negative 1239 kilojoules. What's my total? Negative 339. Okay. Just waiting for numerous people to say that. Okay. So why is this negative again? Exothermic, and that's the CCl bond that's forming, or it's also releasing energy. So who's higher in energy, CH or CL?
OCL.
Look at the magnitude still.
Oh.
Why is this one higher in energy? Which has a higher bond energy? CH, right? Because it's 413 versus 339 absolute value. Why the heck is this one stronger than this one? Okay, so it's closer, so it's greater force of attraction, right? C to CH, this one's small, it can get pretty close. C to CL, atomic radius, a little bit larger than hydrogen, because just some of the energy level differences. There's a first energy level and there's a second energy level. This one can get closer, so its bond energy is higher. This one can't get as close, so its bond energy is a little bit lower. Yeah.
It's always going to be the 413.
And it's usually, unless there's a weird situation, but they always take an average. These are all averages. Okay. So remember, delta H normally is taken by getting your delta H normally. If you just have delta H information, you do delta H what minus delta H what? Products minus delta H reactants, and that's the summation of those energies, right? When I say summation, what am I actually considering? Okay, so I'm adding all products, delta H's of formations together. But do I just add them together? What if I have 2 or 3 of some products? You multiply the numbers. Okay, that was a mistake we made in our thermochem test, so I just want to make sure. So we're adding all the products, delta H's together after the multiplication with the moles of that certain product. Same thing over here, but you're adding your reactant energies of delta H formation after you've added or taken into account the numbers you have of them. So that's our normal delta H of formation, or delta H of reaction. When we're doing bond association energies, what do we do? Broken minus formed. Who are broken? Reactants or products? Reactants. Who are formed? Products. So you see it's flipped, right? This is the only time where we have this difference. So energy required to break bonds. This is delta H of reactants, which is the energy it takes to break the reactant bonds. Summation minus summation delta H product bonds, which is the energy that is taken in or released. Come on, AJ. Released. Okay, so this energy is released, hence why we have the negative already here to indicate that. Whereas this energy, which is energy of reactant bonds, is going to be, what's the word that means endothermic? What's the word that means taken in? Absorbed. This energy is absorbed or acquired while this one's released. So just make sure that you remember that they're always published as positive values, because when I say the word bond dissociation energy, I'm talking about the energy it takes to break a bond, no matter what. That's just how we call it. But when we put it into our equation perspective, that negative offsets that to allow us to see that as a released amount of energy. So overall, that's a quick review, and then we're drawing Lewis structures. So take maybe 15, 20, grab one of these guys, grab one of these, work with them at the answer table. So I'm going to write a reaction first with combustion, and on the back it's going to have some hybridization stuff. Four. I want to hear you guys talking about the chemistry here. Talking about the chemistry. Completing the worksheet.
You're on. We were on equations and so. Okay, go ahead.
Did you get like negative 2270? 78, sorry, I'm doing it based on
Oh,
estimate.
it's
Because mine's half of that.
So negative, oh, 2270?
Yeah.
Oh, yeah. Okay, I thought you said,
22, sorry.
I thought you said 200, like 22,000. That's not possible.
Oh, no,
But it,
Go ahead and do number 5. You got this.
oh, that's right, that's right.
If you get done with that, move on to the back. And then after that, we'll be moving on to our lab.
Okay, so the back, and number 5, where do you get
Uses that table. Uses the table there.
You say possible?
No, yeah, turn over. Good. It uses that table 6.2 right there. Yeah. Do that. I'm gonna change this because everybody else did the other way, so I'm showing you this way too. I hear you, Calvin. Hold up. I get a little bit on the distracted side. I hear you, but I just did not hear you though. Yep. I'm talking about a lunch and finish this, please. table, a 6.2 table.
But don't we need like equations that eventually add them to the final equation?
Hess's law comes in 3 flavors. Delta H is equal to Q over moles. Delta H is equal to summation of delta H equations, like equation 1 plus equation 2 plus equation, or this is Hess's law too. This is Hess's law. H of reaction equals summation of products minus summation of reactants. Yeah, Hess's law can mean many things.
Okay.
Oh yeah, I'm demonstrating the 7/2 one for you guys.
Oh.
You'll all work out this. I'll show you how to change it.
7/2.
This bottom one. You're combusting 2 moles. I'm combusting 1 mole. It's gonna be double. All right, eyes up here for me, guys. 5, 4, 3, 2, 1. All right, I don't think anybody did 7/2, so I wanted to demonstrate this one for you. Raise your hand if you did just 7 as your ratio for oxygen. 7 in your BCE. Did you do 7/2? Okay. So in thermochemical equations only can you do fractional coefficients. So I wanted to show you this so that you could remember that was an option. So you drew your structures out, you counted up your bonds. Yours will be double than mine and Alvin's, but that's okay still, because in the end you'll just say you combusted 2 moles of ethane versus we combusted 1 mole. So whenever you see this value as positive and you see this value as positive, why are these values positive in number 3? What are they expressing? Bond dissociation energy. This is the bond dissociation energy of all of these bonds on the reactant side. This is the bond dissociation energy of all these bonds on the product side. But what we do is we subtract them to show the difference. So when you do subtract them, the bonds broken minus the bonds formed, or reactants minus products, you do get a negative number. So what does that mean about this reaction? Exothermic. So it releases about 1,000 kilojoules for every 1 mole of ethane. So you guys who did 2, you combusted and you produced double the heat or double the energy released from every 2 moles of ethane. So you could use it as a ratio. So when I say per mole, kilojoules per mole, that means per 1 mole. So you guys probably published yours without that per mole thing, just as kilojoules, because you're showing that that reaction that you had created that amount of energy. So be careful when you put per mole and when you don't put per mole. So that's per 1 mole of ethane. And so that means it's exothermic. So what would it feel like to you if you were holding that container as it was combusting? It'd feel very warm. Combustion is always exothermic. That was a question we missed on our end of our exothermic test. Lecture chem test. Anytime you're combusting something, it is going to be exothermic. It's going to have a negative delta H. So I left 5 hanging here because I want you guys to remind me. Whenever you're doing a Hess's law version, which comes in 3 flavors, like I was just telling Sean, this is H products. H of formation of products minus delta H of formation of reactants. So I have my 2, what is this, what is this? CO2s? Yeah. So now we are looking at individual bonds in the first part. Now we're looking at individual molecules in the second part. So 2 CO2s inherently have that amount of energy. 3 waters, and like your ratios will be different. It'll still work out in the end. Had that amount of energy. This is the energy of. This is the energy of ethane. What am I missing? Okay, so what am I still going to write there to get my points in the AP Chem exam? You still will write 0. So this is my sum. Oops, that's supposed to be adding a negative. Adding a negative 241, and that's subtracting a negative, okay? And so plus 7/2 times 0 for my free element of oxygen, because that will give you a point on your free response questions most of the time. So when you take your products minus your reactants, what do you get? And I'll write what I get. What do you guys get? -2. Let me fix that. -2,855.4 kilojoules. I got negative, basically. This was per 1 mole, and this was per 2 moles. So why, though, still, are these not exactly the same? They're talking about the same reaction, right? Heat of combustion, heat of combustion. What happens is we determine the bond average energy from many molecules. When they're in different environments, they might have a slightly different bond energy. So this negative 1100 basically versus my negative 1400, that's a difference of 300 kilojoules. That's because we've taken a lot of data to determine the delta H's of each of these molecules and a lot of different data to determine the bond energies of these. So we will have a discrepancy, however, they're both expressing exothermic, so we're in the right place, in the right volume, okay? So that's kind of to show you that sometimes you'll have different answers based on the data that was used to create that data table. Alrighty? Alright, so last thing for now, go ahead and do the FRQ on the back. It's hard to see, I'll pull it up on the board. You guys can talk to each other about it. And specifically focus on the things that you're struggling with. So on our ketone here, C in the middle, O double bond in the middle with it, that's a ketone. So that's why it's called propanone, because that's our ketone. So I'm trying to review some organic as you go, because you don't have to memorize the organic, because you really just have to draw a Lewis structure that's valid, and it shows you the structural component with the oxygen in the middle attached to the C. Remember how it's written out? It kind of tells you where the attachments are. So we have our C in the middle, this C to this C to this C, they're bonded. This carbon in the middle has how many electron domains? Okay, so it's 3 electron domains, so it's what hybridization? sp2. Well, regardless, if it's got 3 electron domains and there's no lone pairs on that central carbon, what's the shape of that central carbon? Trigonal planar, and if you're thinking trigonal at all, you're probably thinking 360 divided by 3 is 120. And so trigonal planar is definitely going to be approximately 120. If you put on the AP exam 120 or less than 120, they would give you credit for your bond angle there, because like Alvin was saying, these lone pairs are huge, and so they'll push down and repel that central carbon to create a little bit more repulsion. The next part, predict why the delta H VAP is different. So this is talking about IMFs, okay? So you have to know if something's polar or nonpolar off the bat. So propane, think about how does it look? 3 carbons, 7? No, 8 hydrogens around it. Polar or nonpolar? Nonpolar all the way, okay? So propane is nonpolar. You are writing this down for yourself because I'm about done with IMFs with you guys. We're going to pick up more IMFs next week. And then propanone is, look at the structure, polar, nonpolar. Definitely polar, so propanone is definitely polar. So at this point, we're going to start talking about IMFs here. So propane, which is nonpolar, experiences what form of intramolecular force? Say again? London dispersion. You should have these memorized. Okay, so propane is nonpolar, experiences a London dispersion force. Propanone is polar, but look and see why it's polar. There's a C to O bond, especially with the lone pair on top, very partially negative. What kind of IMF will it experience? Why dipole-dipole, not hydrogen bonding? It's not hydrogen bonded to bond, okay? And then propanol, all means what on the end?
All.
An alcohol, okay, so there's CH3CH2CH2OH. Here's our alcohol in the end, double bond here. What kind of experiences will it have? Anybody? Sorry, is it polar or non-polar? Is polar because you have a very partial negative out there at the oxygen end. So it's polar, so what kind of IMF will experience? So hydrogen bonding, okay? Because it has a hydrogen bonded to F over N. But however, the part that we were just describing were all the predominant, the main forces that's forcing these things to interact with each other very strongly. So do not forget that if you have London dispersion, that's because you're nonpolar, you don't have any other IMF in action. If you're dipole, as I did not draw, no, we did draw this. This is what Kirk drew. So looking back up here, which piece of this molecule is experiencing dipole-dipole? The CO in the middle. So if I had another propanol drawn here, it would interact through dipole-dipole. But what about this segment here and this segment here? These represent kind of what part? Are these polar or nonpolar over here? These are nonpolar. So how do they interact with another propanol coming in out of London dispersion? So you should remember these are cumulative. So you have dipole-dipole and London dispersion in action on, even if it is a polar molecule, just the polar component of it will interact via dipole-dipole. The rest of it that's considered nonpolar, because we're starting to draw big structures here, they will experience London dispersion. And then our last one, hydrogen bonding, where is that occurring here? Where is it occurring on here? Just right here. Just when hydrogen bond is kind of scooching here and attract this side. So what's happening all over here? Yeah, London dispersion forces will hold all the CH kind of areas together. So there's actually some dipole-dipole and London dispersion, because usually once you have hydrogen bonding, you also can have other things that are just simply polar, not hydrogen bonding polar, but polar coming in and interacting with this side as well. So basically what I'm showing you here is that propanol has a lot of forces holding propanol molecules towards each other. Then it asks you to express how does that relate to delta H VAP. What the heck is delta H VAP? What is heat of vaporization? What does that mean? Okay, so I'm hearing delta H VAP means liquid to gas. So I want you guys to draw that. Draw anything going from liquid to gas. Do not just draw like a cartoon picture, draw blue stuff. If you want to do water, do water. It might be easier to draw than one of these. So I want you to draw liquid water, how it would look on like a particulate diagram, and then gaseous water, how it would look on a particulate diagram. Yeah, that's what I want to see then. Is there the orientation or the arrangement towards each other? So in your liquid, they're condensed, they're close together. What's happening between these water molecules? Hydrogen bonding, right? So the O lone pair attracts to the H, and the O lone pair attracts to another H, and the O lone pair attracts to another OH. And they can do it doubly because there's two lone pairs there. So there's a lot of attractions going on here, right? Lots of attractions. How about over here? In their gaseous phase. Right, so basically, I'm going to say almost none. So we've overcome most hydrogen bonding IMF interactions. So it takes energy to overcome that amount of attraction. So it's definitely going to be an endothermic process overall. It's going to be, we're putting energy in to overcome the attractions. So why is delta H VAP different for propane versus propanone versus propanol? It's all prop stuff, right? Why is it different? When you say bonds, do you really mean bonds?
The attraction.
The attractions get stronger. Okay, so just make sure we're using the word bond where we need to. So yeah, I think that's what you're saying too, Courtney. So this one has the lowest delta HVAP, propane. This one has the second lowest. This one has the highest because of the intensity of the interactions between them. Do not say bonds unless you're saying hydrogen bonding, but you're still using it as the word attraction. Because if you say the word bond and you say break bonds, you will get no points on this question whatsoever because they will only assume that when you say break bonds, you're talking about breaking these bonds here. Okay? I'm trying to train you to answer this because that's been one of the hardest things to get people to say right. All right, so then my last question. Oh, isomer. Okay, did anybody figure out the isomer? What if I said draw an aldehyde? What's an aldehyde? Ketone has a CO in the middle. Got it on the end. So you write CH3, CH2. How do I write the aldehyde? How do I draw that? A C, a double bond O, and an H on the end. That's an aldehyde. So an isomer is the same formula, different structure. So you couldn't have drawn anything with a double bond O in the middle because we only have one carbon, it would have been the same structure as that. So you could either draw your aldehyde on the left or on the right, but either way it would have been the same formula, different structure. And this one can still do dipole-dipole interactions as well. And then my last one, I think Emma got me here, SP, because there's how many electron domains on that carbon? 2 electron domains is SP hybridization, and then there are 6 sigma bonds and 2 pi bonds. Because you count all the singles or the first bond laid and the intranuclear axis is a sigma, and then the last 2, which were on the double bonded side of things, triple bonded side of things, as pi bonds. That's a great FRQ to study, okay? Check it out for yourself. All right, so I have 15 minutes left. Time flies somehow in this class. So the lab you guys read, you have 5 minutes or so to do the pre-lab. You'll be working in teams of 3 for this lab. So go ahead now, form doing teams of 3. And I need to pull Arshia, not Arshia. Chidu or so Vinky and Arushi are gone for one person here. You have 30 seconds to decide on teams. Mix it up some. So do not go with your normal people. You have one person that's your normal, if that's what makes you feel comfortable. But you need to pull in a new group member. And go. Yeah. Because we have a lot of people this year. Alright, you have 5 seconds to get a partner. And sit near them now. 5. Switch to the lab station if you need to. 4. Oh. 3. If you do not have a partner, Vinky and Arushi will be your partner. Courtney? Vinky and Arushi. Yep, because they're both out today. Okay. So Courtney is Vinky and Arushi. You guys can be the others fine. Okay? That's fine. It works. Alright, as you look on the lab sheet, look at the pre-lab reading. Complete the first 2 questions. You have 5 minutes. Write this on a piece of paper someplace. Yeah, so
I will be right back. Oh, I'm gonna feed him this. October 20th. Forward if you done this class, I don't know. She gave me an answer right now.
And you got time right now to do your pre-lab.
two type of bond.
I've been explaining. Assigning which bonds have prime.
Let's put down
So, and you guys text them, you have the numbers in the groups.
Alex, we have Zink's just a metal. What's the bond to? You can replace it. Scratch it out. Don't want to have that on
Courtney, before you go, let me give this to you. It's your homework from the other day.
Let's go high.
No, I want to do the highest. And then,
Moving off there. So you have to read it all? Well, that's terrible. So, this one. You're gonna be
alright, that means that your first part should be mostly done. So let's talk about this before I let you continue, okay? So what's this whole goal? What's the whole goal of this lab? You guys read this weekend for me. Louder? How would you do that? Okay, so you'd be checking out physical and chemical properties of an unnamed substance to determine its identity or the classification bonding type it falls under. Do you guys feel like you know enough to do that?
Yeah.
You have a lot of background knowledge. And I will train you tomorrow. I'm going to give you 6 known compounds, and I'll tell you what it is. I'll tell you it's a ionic, metallic, polar covalent molecule, or a non-polar covalent molecule. And you will run tests to get some verification tests under your belt to say, okay, this is how conductivity should work, this is how solubility should work, this is how this should work, this is how that should work. And I give you a plethora of materials that you can use. You can see on the sheet there are tons and tons of materials. So it's a material heavy lab. After I train you tomorrow so that I feel confident in your abilities and you're not doing anything stupid like catching things on fire you shouldn't be, test for flammability, then I'll make sure that I trust you enough to run the student directed lab on Wednesday. So tomorrow we're doing teacher directed, then you were crafting your own procedure on how would you run 10 to 15 probably tests, and how would you know if it's proving to be true to that property or not true to that property. And so then Wednesday, I'll give you 4 to 6 new compounds, and you have to classify them, and then you have to identify at least 2 of them with certainty. Like you put your firstborn on there, okay? And that's going to be using a lot of the background knowledge you gained so far in our chemistry lab together, okay? So, homework for tonight, 4 FRQs of the 9. Do you know where the FRQs are? They're in your packet, okay? You guys still have 5 minutes to finish that pre-lab right now. Can you finish up anything? Or you will do 4 of 9 FRQs. Thanks, Stallings.
Any 4?
Any 4, yeah,
Like,
because I just want
stuff
to
all the way
page
to
you. There's some that are long and some that are short.
What was up? It's like we get stuff in the first like part A, part B of the question. Like we just like I don't know how to start that question. Just make your different.
That's fine. I want to see about half.
That's fine.
Alvin, pass these out. Electric chem test corrections are due tomorrow as well. I got a couple of those.
I thought once it was Friday last week. I was chilling in my house. You lost it. Cool.